So while we are going to continue learning new things, we're about to get started on a whole bunch of consistency with equilibrium constants, and more equilibrium constants, and ice tables and rice tables and ice boxes and more. But let's talk about something related to but different from an equilibrium constant real quick. I promise we are going to go with consistency here. We said equilibrium constants are products raised to their coefficients multiplied together divided by reactants raised to their coefficients multiplied together. So there's my Kc expression for this reaction, which was where we left off with our last video actually. And we solved for the numerical value of Kc for this reaction. It was 3.05 if I remember correctly. I don't have the notes right in front of me. What if we have the same expression and we plug in these values? What are these values? Well, in our rice table, ice box thingy, we had an initial row, and the initial concentration of I2 was 1.5 molar, and the initial concentration of Br2 was 2 molar, and the initial concentration of IBr was 0 molar. So we've actually plugged in initial concentrations down here. So if I plug in initial concentrations, we're going to call that thing QC. Kc is an equilibrium constant. QC is called reaction quotient. So QC, reaction, I can't talk and type and talk and write at the same time, quotient. QC is really any time other than equilibrium. So it does not have to be only the very initial stuff, but any time other than equilibrium. Well, let's look at one of our favorite little plots. It's KEQ over here in the equilibrium region. It's Q over here in the kinetic region. So the way that you write the actual expression is exactly the same. Products raised to their coefficients multiplied together divided by reactants raised to their coefficients multiplied together. Have you heard me say that enough times? The way that you write these two are the same. If it's in the kinetic region, it's called Q. If it's in the equilibrium region, it's called K. Reaction coefficient, yep. Sometimes we will calculate Q so that we can compare it to K and decide what happens to our reaction. If Q is smaller than K, that means that Q needs to grow to be bigger. And the way I think about this, I really think about this every time. I don't memorize what I'm about to tell you, or I don't memorize the Q greater than less than kind of stuff. I just realize that Q needs to grow. So that means that my numerator needs to get bigger in order for Q to equal K. So that means I need to produce more products. When Q is equal to K, it's at equilibrium. So I need to make this Q bigger in this first instance to reach equilibrium. So I produce more products in order to reach equilibrium. When Q is when Q is greater than K, said that backwards, sorry. When Q is greater than K, this Q needs to shrink in order to be the same value as K. So that means that the reactant concentration, the denominator, needs to grow in order for your overall value to get smaller. Really, truly, I do not memorize these things. I do know Q equals K at equilibrium. I think through, does it need to grow, does it need to shrink in order to match K? And growing or shrinking, I relate to numerators and denominators, products, and reactants. Really, truly, I hate memorizing. If you like it, that's fine, do it. But I hate it, so I'm going to think through the way I just told you. Okay, what do we do with this? A container with the following initial concentration is prepared. Which species do we expect to increase when the system approaches equilibrium? So what have we been told? We're told Kc value, which means at equilibrium, this is the case. We're told some initial concentration values, meaning not at equilibrium, here are some concentration values. So if we need to calculate Q so that we can compare Q and K to see which way it goes, we need to start by writing the Q expression. The Q expression is the exact same as the K expression. This is where I'm talking about consistency. Products raise their coefficients, multiply together, divided by reactants raise their coefficients, multiply together. That's a 2. Raise their coefficients, multiply together. So all I do is a little plug and chug. 0.48 squared divided by 0.6 times 0.76 cubed. and I get 0.874. So QC is 0.874, and K is 1.2. 1.2 compared to 0.87. I do believe K is greater than Q. So that means Q needs to grow in order to match K. If Q needs to grow, that means my numerator needs to get bigger. That means reactants will be converted to products. We will start making more products. So that means the concentration of NH3 will increase. Did you understand all that reasoning? I hope. Okay, cool. Let's do another problem. Problems and problems and more problems. At the high temperature of a car's exhaust system, the following equilibrium is important in pollution. This one. If the initial pressures of N2 and O2 are this, what's the pressure of NO at equilibrium? How the heck do I start? I'm going to write a rice table, an ice table, an ice box. A rice table begins with the reaction, and that's N2 plus O2 yields 2NO. The initial concentration. For ice tables, rice tables, we will almost always put concentration values in our initial thing here, molarity. However, pressure can also be substituted down here. So we're going to put in our initial pressure of N2 is 0.5, and initial pressure of O2 is 0.5. Initial pressure of NO is 0. And we're going to change some, lose some, gain 2, minus x plus 2x. And at equilibrium, if you want to fill this all out as in 0.5 minus x, 0.5 minus x, 0 plus 2x, you can, but I will often skip that and go straight to equilibrium in terms of atmospheres. And that's gotten a little sketchy down there, but let's see if I can fit it in. I've decided I can't fit it in. So if we go to our next slide and write the KP expression, because I'm going to be filling in partial pressures here, that would be the partial pressure of NO squared divided by the partial pressure of N2 times the partial pressure of O2. Not a Q, that's an O. O2. So then if I fill in my ice table values for that, that would be 2x squared. Note, I put it in parentheses because 2x squared like this and 2x squared like this are absolutely different numbers. 2x is all squared because 2x is equal to the partial pressure of NO2. Okay. So partial pressure of N2 is 0.5 minus x. 0.5 minus x times 0.5 minus x. Well, that's really 2x squared over 0.5 minus x squared, right? That's equal to Kp. We were told the Kp for this reaction, so set that equation equal to the Kp that we were given. I already forgot it. What was it? 0.027. 0.027. And I can start out solving this by taking the square root of both sides. So that gives me 2x over 0.5 minus x equals square root of 0.027, 0.164. And not only could I not fit it in that corner, I can't even fit it all on this slide. Gotta keep going. So I multiply both sides by 0.5 minus x, so 0.164. You may not need to write out all of this math, but I'm writing out all of this math to make sure you're following along with me, at least for today. So that becomes 2x equals 0.082 minus 0.164x. So that becomes 2.164x, because I add 164x to both sides, equals 0.082. So that means x equals 0.082 divided by 0.082 divided by 2.164. That means x equals 0.038. So all of that work to find that x equals 0.038. Now we go back. What's the actual question here? What is the pressure of this at equilibrium? The pressure of this at equilibrium is 2 times 0.038. And so 2 times 0.038 makes 0.076 atmospheres. So that's the actual answer to the question they asked. But while I'm here, we might as well fill out the rest of this rice table. So that's 0.462 because x equals 0.038 and 0.462. So sometimes you might be asked a question like this one, what's the pressure of one of the species at equilibrium? Sometimes you might be asked in a gas question in particular, what's the P total? What's the total pressure in the flask? So that would be take this whole equilibrium row and add up all of the pressures. But we haven't been asked that, so we're not going to do that. But I'm just telling you might see it. Okay. In the lab, this many moles of NaCl were placed in a 1 liter flask and allowed to react. At equilibrium, the concentration of Cl2 is this. What is the value for Kc? What the heck do I do with this information? When in doubt, make a rice table. It's going to work. Make a rice table. So my reaction comes first. My initial comes next. So 0.2810 moles divided by 1 liter, because this is initial molarity, is 0.2810 molarity, because it's 1 liter. That's real helpful, right? That's real illegible. None of this and none of that. Minus 2x plus 2x plus x. Okay. That's all we've been told in our first sentence. But then, this is helpful. The equilibrium concentration of Cl2 is 0.137. 0.137. So that really means x equals 0.137. Whoop, whoop. So 2 times 0.137 is 0.274. My stuff gets crammed together a little bit because I'm a big writer. 0.2810 minus 2 times 0.137. This becomes real small. 0.007. 0.007 molar. That's tiny, but it's not 0. Equilibrium must have some amount of all products and all reactants present at equilibrium to be considered at equilibrium. It can be a really small number, but you have to have some of everything, reactants and products, in order to be at equilibrium. Oh, I got a little distracted and almost left off this video without even answering the question. What's the value for Kc? That's what they were actually asking us. What's the value for Kc? So I'm going to write a Kc expression because that gets me points if I can't do anything else. NO squared times Cl2 divided by NaCl squared. So then I just fill in my concentrations, 0.274 squared times 0.137 divided by 0.007 squared. Do the little math and you get 209.9. So what's favored at equilibrium, products or reactants? You'll have to answer that. Goodbye.